So remember how in the previous units we looked at like the purpose of an operating system. So at a very high level, the operating system makes it easier for users to run different applications on top of the raw machine. Now we're going to actually see some demos of like how the operating system does that for you. So remember that in your laptop or your desktop machine, you have a limited number of processors, right? But at the same time, on our laptops, we all run like sort of like an unlimited number of applications, right? So we open up Outlook, we open up Word. We never have to sort of like, as users, we never have to worry about like, oh, like is the one processor that I have like already being used? Like, can I open another one? So we never have to worry about that, but we do have a limited number of physical processors. So the OS, the operating system, gives the illusion of having an unlimited number of processors, so that like you can open up whatever application you want and it will run on the physical processors. So how does it do that? There are other abstractions that the operating system provides. For example, most applications, or at least users, don't have to worry about memory. Like the operating system makes it seem as if there's an unlimited amount of memory, even though there is like a very limited amount of DRAM on that physical machine. And the same goes for storage. Like you have a file system provided, and you don't have to worry about like where is bit 1 being stored, where is bit 0 being stored, and so on. Okay? So now we're actually going to see demos of how the operating system is actually doing all of this for you. So let's take a look at our terminal, and here we have like several C files that we have up to sort of like show you what's going on. So first, let's take a look at this file called cpu.c. Right, and it's a very simple C file. What it does is it gets a certain string from the user, and then in an infinite loop, all it does is it prints that string, it delays for 1 second, and then it does it again. So it's just going to be, so for example, let me compile that. It's already compiled. By the way, one of the nice features of a makefile is if you have not changed the file that for example, CPU is dependent upon, it does not recompile. So for example, let's say I do this, right? So now I've changed cpu.c. Now when I do make CPU, it actually doesn't. Sorry, that was sort of like a mistake. But if we change something here, right? Let's say we add another space, right? And now when we do this, this is actually a bug in my makefile. Sorry about that. So what I'm actually including here is that there is this executable called CPU that we want to produce, which depends upon this file cpu.c. Similarly, there's all these like different things that we're going to show in the demo today, which depend upon different files. So if we go back now and we say make CPU, now it actually recompiles CPU. But now let's say I try to do that again, it says CPU is up to date because I've not changed cpu.c. So now I've actually changed cpu.c, or changed the last modified time of cpu.c. So if you do make CPU, it again recompiles. The beauty of this is that you could have a very complicated project, like hundreds of different files with different people touching different files. And when you do make, it will make sure that only the part that needs to be recompiled will actually get recompiled. So it's a beautiful system, something that you should get familiar with as you do more systems work. Anyway, back to topic. So we have compiled our cpu.c, and so we're going to run it with, like, let's say hello, right? So all this is doing is that on this CPU, it's running like hello in an infinite loop, hello, and so on. Let's open up another terminal into this same machine, and what I'm going to do is I'm going to run, let's say, CPU with world. Now you can see that both of these applications programs are running at the same time. Like hello is being printed, and so is world. But we have only like one physical CPU. So what is actually going on? So this is what I said, what I meant when I said the OS provides this illusion of being a number of processors, even though there's only one physical processor. There's only one physical processor which is doing both the hello program and the world program. And in the rest of this course, you will learn about how the operating system actually does this, right? So that's how the operating system that's a demo of like the operating system virtualizing the CPU. Let's actually look at how it virtualizes something else, memory, for example. And so let's make the memory file. It's already up to date. So let's do this, right? So in this particular program, what is going on is that it is printing the address of a pointer pre, which is in some location which ends with, let's say, 520. And then that pointer has a specific location in it, which is like ending with 51C, and we are simply printing the value stored in that location, which is whatever value we send into this program, right? So let's actually take a look at the program itself to see if like this makes it better. So we have the program, we have the pointer p that I talked about, and then we have a variable x, and then p holds the value of x. Right, so p is a pointer to x in C programming, and what we're doing is we're just printing the ID of the process and the basically the address that is stored in p and where p itself is located, and the value inside that address, right? So to actually draw a little bit of a diagram here, so sorry. So let's say, so there is x, and then p points to x, right? So p is a pointer. So when you say what is the value of star p, that's actually giving you the value in x, right? So what we're seeing is like we're printing the address of x, we're printing the address of p, and then we're printing whatever value is stored in x that we're accessing through p. The point of all this sort of like complicated stuff is to show you the following. So anyway, now that you understood what the setup is, let's do this again. And then, so again, what we're seeing is that, so we see that there's a certain address for the pointer. There's a certain address that is stored in the pointer 51C, and the value that is stored in 51C is 100 and 101. It gets incremented every time there's a second, right? So long story short, in address 51C, we are putting values like 100, 101, 102, and so on. Let me just let this program run, and then what we're going to do is we are going to access this program again from a different terminal, and then we're going to put the value 10. So if you look at the address where that's going to be stored, that's 51C once again, and then this time it says the values is like 10, 11, it's like it keeps incrementing like that. However, here's the trick. Both applications are running at the same time. So if you stopped each application and asked it like what address are you printing, like where does 101 reside, it would say 51C. If you stop this program and ask like where does 17 reside or 18 reside, it would say 51C. So the same address is being seen by both applications, and we are writing different values into both applications, and apparently it doesn't cause any problems. Right? So this is what I meant when I say the operating system virtualizes memory. Every application thinks it owns the entire space of memory, and it can do whatever it wants. And this is true for every application. Like, so every application gets this particular address, for example, 51C. It can write whatever it wants to it. It does not affect other applications that are running at the same time. Even though in your physical memory chip, there is only one location which can hold only one value at a time. So again, like how does the operating system do this? So this is called memory virtualization, and it's a very interesting topic that we will get to later in class. Finally, there's one other thing that I want to show you, which is basically I/O virtualization. So we have this program which does something very simple. So it opens a file, and then it prints hello world into it, and then it writes it to the file. That's all it's basically doing, right? So we have a character buffer, and then it writes hello world into that buffer, and then it writes that buffer into the file. So long story short, we are writing hello world into this temp file. That's actually what is going on, right? Now you might imagine like, oh, this is like really simple. Like we open the file, we write hello world into it, and we finish up. However, again, the OS is hiding a lot of like different stuff from you, right? So for example, let's compile this stuff, right? Now what I'm going to do is I'm going to use a nifty tool called strace. So what strace does is it traces all the different system calls that occur as you run a different program. It's very useful in a number of different ways. Like your program, for example, could be written in Python or C or Java or whatever. It always ends up in system calls, because system calls are the language in which you talk to the operating system. We haven't really covered system calls in depth yet, but we will very soon. So anyway, to make a long story short, when you execute this small program, like these are all the different system calls that get executed, right? And if you look at here, like like this hello world actually being written, but it's like so many things must happen before you actually get to that point, right? There's actually like even more complexity. I don't know if we'll actually be able to get to it. Let me see. So this particular folder here is it's for debugging different kernel events inside the kernel. So for example, when this application was running, you wanted to know like like what else was like actually going on in the system. This is how you actually go look at it, right? And let me see. So if you look at trace, for example, right? This is all the different stuff that happened as you basically wrote hello world to the file. So we are not going to get into all these details, but there are like system calls like like VFS write, sys write, and then here we are actually seeing that a system call is being called, and there's lots of different functions that get executed as you go through, and then at the end you basically say, oh, it's all complete. But if you look at it, there's over 2,000 lines in this particular file, all of which had to execute to enable you to write hello world to that file. So with that, I hope this provided a good flavor of like how virtualization is going on in the operating system, how the operating system provides this illusion of being like unlimited number of processors, unlimited amount of memory for each process, and how it hides a lot of the complexity of actually writing to storage.